watch party. Done, yes.
Say cheese. Cheese is.
احنا لايف.
شو ها؟
احنا لايف.
اوكي.
لا.
شو؟
يلا انا I will introduce you بس عم بمشي. Yes, workshop day 1. Dash Rawad Mezher. Yes. Yes. Perfect. Close.
Okay, so welcome back for this afternoon session of QICA. And now we are going to have a talk by Rawad Mezher, PhD student between the Lebanese University and this QICA.
So, thanks, Joe. First of all, good afternoon, everyone. I hope you're enjoying the workshop as much as I am. I hope everything's going well and you're having a nice time. So I wanted to speak this a bit like this emotional speech, but then, so just to say, 3 years ago, I wouldn't have dreamed of working in quantum information, but now, like 3 years ago later, we're here doing the first workshop on quantum information in Lebanon, which I think should be something to be proud of. So, without more sentences, I'm going to start with talking about what we're going to do. So this is some work which we've been working on for the last year, about a year and some months. So it's called Efficient Unity Design for Partially Invertible Sets and Application. So it's joint work with Damien, Joe, and Joseph Trem. And so before we start a bit, I'm going to start by introducing the various technical concepts. So this is going to be a bit different from the talks that have been like previous. It's going to be a bit technical. So I'm going to start with introducing these technical terms, such as what is hard randomness, what is unitary T-design, what is MBQC, and notions of classical simulability. And these things which are apparently not linked together, I'll try throughout this course to see how, to show you how they link together and how they sort of fit in this picture of what we're trying to do. Then we're going to define, so these are basically the objects which we're working on, these so-called partially invertible universal sets, and how these things can give you efficient design. And then we give an application of these in terms of architectures which demonstrate what one would call quantum supremacy, or in more general terms, quantum speedup. Finally, we're going to talk about this conjecture which so these partially invertible sets and stuff, there's therefore specific structure behind this. But what about the general case? So we're going to examine this general case in sort of analytical and numerical way, as well as the end states of ongoing and future. Right. So first of all, to start with hard randomness. So from the name, it's random quantum stuff. Okay, but more than that, it's a bit more technical than that. So hard randomness, the way I like to think of it in this very rough way, is this sort of uniform distribution, like this uniform random distribution over the unitary loop, modulo a little bit of technicality. And so places where this hard randomness is useful is in state randomization. So it's shown that averaging over certain statistical moments with hard measure gives you something which is a completely mixed state. And this completely mixed state is good for information hierarchy. So when you It's used to estimate fidelity in some benchmarking protocols. So when you want to estimate the quality of whatever quantum thing you're doing, usually there's a process of doing this, which is called randomized benchmarking. And the way the quality is estimated is somehow related to this integral of the second moment of the Fanar measure. It's used also in the generation of generic entanglement, so typically entangled states. So here, if you evolve your system according to unity, then you can show that your entanglement is what we call generic or nearly maximal. This thing has some application in circularization, in understanding how quantum systems reach their equilibrium. And the thing I'm going to talk about a bit more in detail is one of the applications of our technique, the quantum speedup protocol. Right. So what are unitary designs? So you can think of it as a sort of randomness of the unitary group. It's a random sampling process of the unitary group, such that the unitaries in this random sampling process have a particular structure. Why do we need them in the first place? Well, because what I was first talking about was hard randomness, right? So why do I introduce this unitary design? Well, because sampling from the hard measure in general is a difficult task. It requires a number of gates, like a number of processes, which scales exponentially with your system size. And this, in computer science standards, is something which is bad. So how do you solve this problem, essentially? Instead of using the entire Haar measure, what you would like would be to mimic sampling from this Haar measure up to teeth order in your statistical moments. And this is exactly sort of the definition of the unitary T design. It is a random distribution on the unitary group. It's usually finite, and not necessarily everything. And it's arranged in a specific way such that whatever you're sampling from is mimicking sampling from the Haar measure up to a given order. And so the main advantage of these unitary T designs is that these can be sampled from efficiently. Right. So maybe to introduce how many classes of random T designs we have. So what I said that now is basically we're mimicking sampling with respect to Haar measure. So we can do this in two respects. We can do this in an exact way, and these are called exact designs or group designs. Now, these rely on specific group theoretic constraints to be applied on your ensemble of unitaries which you have. And these group theoretic constraints are not trivial to obtain for orders of T, which is the order of the statistical moment, which are higher than 3. So we know that a particular group, and quantum information is a 2 design and a 3 design. It's called the Clifford group, but we sort of don't know higher examples of higher order designs like T equals 4 designs. The Clifford group certainly is not, and we just don't know how to get this, how to find higher order designs which satisfy this group theoretical constraint on the structure. So instead of, and anyway, in most of the applications, you don't even need exact mimicking. What you can do is you can mimic approximately the Haar measure. And this is sort of the concept of epsilon approximate T designs. And this thing is what I'll be talking about in the rest of this talk in detail. Right, so fairly rough, maybe a bit too vulgarized way of describing what a T design is the following. So what you get, what you have is that it's a set of unitaries, UI. What I mean by unitary is a unitary matrix. And with every unitary matrix you sample inside this set, you sample it with probability pi. And you're allowed to apply T copies of this unitary to your input state. And what you get at the output is an output state which you cannot distinguish whether or not it's Haar sampled when this T is sort of less than the order of the design. So when I first start talking about designs, I say, for example, I define, for example, design I'm working with the 4 designs, for example. So what I can do is say if I have 4 designs, I can use 1 copy, I can use 2 copies, I can use 3 copies, and I can use 4 copies. And still, the output would not be indistinguishable from the output of the Haar measure. But if I use 5 copies, if I promise the 4 design, then it won't work because the randomness would stop, right? Because if you would have an infinite order design, then that's just the Haar measure, and you get inefficient again. So yeah, that's sort of the feel behind how these stuff work. Right, so if you remember the application for the randomness, which I stated at the beginning of this talk, so each one of these applications can be done equally well with an approximate design. So a t equals 1 design gives you state randomization, a t equals 2 and 3 design gives you fidelity estimation, which is the quality of it. And the generation to learn mechanism and quantum speed up, and the t equals 4 gives you thermalization. The application. Right, so there are many constructions of unitary designs. You can basically, so there are many ways in which you can construct it. One of them would be, for example, this type of circuit, which is called a local random circuit. Others would include random unitaries in two different bases, like in the X and Z basis. And others, instead of working on the unitaries themselves, work on what we call their Lie algebras, or the Hamiltonians, which are, so every unitary can be represented as EIHT, where H is its corresponding Hamiltonian. So you introduce some sort of random motion on the unitary group of this Hamiltonian, and you would show that it would converge to a design the way you want it to do. But that's not the focus here. What we're focusing on is a sort of circuit model to generate this unitary T design. So what is, first of all, a quantum circuit? Is defined by a certain number n, which is the number of input qubits you have, and is defined by the depth, which is the number of layers of computation you have. And each layer of this computation is essentially one or more random unitaries which are applied, one or more unitaries which are applied. But in our case, in this local random circuit, these unitaries are random unitaries in the sense that the way the circuit works is the following way. So you start out with a sort of, let's say here, 5-qubit state. And what you would do is that at step 1, you would choose either row 1 or 2, or row 2 or 3, or row 3 or 4, or row 4 or 5 at random. Here, for example, the choice is row 1 and 2. And what you would do is that you would apply a unitary here, which is a random unitary. And this random unitary would be sampled. You can apply it from two types of sets. One of them, you can use the Rawad Mezher on U4, which is not really good. And the other one, you can use a finite set of unitaries, which contains their inverses, and which is universal, and which has no algebraic elements. So if you see, like, the way these are defined are a bit constrained. So this is a very specific type of finite set of unitary you can use. And you can show that repeating this process, what I said, at each step choosing two random rows and applying the unitary chosen from the following set over a number of times, which scales efficiently with your system size, so this is the crucial part, would give you, on the unmeasured output, a unitary, which is sampled from an ensemble of random unitaries. And this ensemble of random unitaries is exactly the unitary T design which you want. And the depth is usually a function of T, the order of the design which you have, of epsilon, the precision of your mimicking, and of n, the size of your system. Okay, so this is going to be a bit uncommon. Does anyone have any questions at this point? Because I feel I went a bit too technical. Feel free. Yes? The Rawad Mezher. It's the uniform measure. So say you have the unitary group, right? U4, for example. What is the most natural measure of, what is the most natural notion of randomness here? You choose a unitary at random, right? This random choice is a sort of uniform random choice over the entire set of unitaries, and this thing is the Rawad Mezher, modulo some additional technicalities that if you multiply a Haar distributed unitary, which is a unitary sampled uniformly, by another unitary which is fixed, you would still have a Haar distributed unitary. So it's a bit technical, but you can think of it as a continuous random distribution, a continuous uniform random distribution. Anyone else? Unitary matrix, like the evolution of quantum systems, the exponential I integral of the Hamiltonian. That's the way your closed quantum system propagates. So a unitary matrix is a matrix which is invertible, which you can go back in time. It's usually defined on closed quantum system. It's the way you propagate your closed quantum system forward in time. Yes?
We have 5 qubits.
Right. let me just go to the previous slide. Do you mean this one? No. This one? Oh, no, right, good. So this raw n is defined as an n-qubit state. It's not a 1-qubit state. So by definition, this thing can be an n-qubit state. And these things are n-qubit unitaries. But this sort of circuit is a particular way of generating. So this is called local random circuit because you're only ever acting non-trivially on 2 elements here. And you're acting, so for example, let's take step 1, which is sort of like unity. So what you have that over 1, 2, right? But this means that you don't apply anything here. So at most, the depth, the number of subsystems which are touched by the unity is at most 2, which is why it's called local random unity. So this is just a construction. Yes, sir. Sorry, I can't hear you. Yeah. Periodicity. What do you mean by this thing? What does this mean? Oh, yeah. No, so yeah. The sort of way these T designs are defined is by taking. So it's a sort of mathematical formulation. So you say that the order of mimicking of the randomness is up to order T in the tensor product. But when you use them for applications, you never really use the order random, the T's order tensor product. You use one unit, which is order tensor product 1. You use one copy. And this one copy, so these definitions in terms of the tensor product give you some freedom in terms of mathematical relations you can use, like the depth of randomness and mathematical relations you can use. And it's these mathematical relations which we manipulate to give us whatever we want for a given application. But we never use the T design in the way that the definition is stated, like by using T copies, because you can't clone, right? So, I mean, in general. And so you don't even need to clone. So this is just one restricted way of defining the design. You can define it in equally other better and more intuitive ways. But I thought this was just like the easier one to go with the calculation. But the idea is that you always, in your calculations, you use this property or you use another equivalent property just to prove some stuff which cannot be proved if you have order 1 moments. Because these order, like say for example you have order 2 moments, these translate to a probability order 4, like to for example x u0 power 4 because of the q cross u. So using the, does that make sense? Sorry? The dimension of the unitary matrix. Here. So here the dimension of the unitary matrix is always 4 because you have 2 qubit systems, and a 2 qubit system is U2. So U4, U2, U2 to the power 2. Okay? All good for now? Good. Yeah. So this model is what we call a circuit model, but another interesting model which we would like to look at, and it can equally be used to generate a design, and it's more physical in the sense that you only require at the beginning a large entangled state and measurements on it, is what is called measurement-based quantum computation. So it's an alternative to the circuit model in which all your necessary entanglement for quantum computing purposes is generated in this large entangled graph state. And what you have here are your nodes, which are the qubits, and these are initialized to the plus state. So plus state is defined as ket 0 plus ket 1 over square root of 2, meaning that if you measure on the computational basis plus state, you would get with probability 1/2 either the 0 state or the 1 state. And you, between these individual qubits, you apply what is called an entangling operation. So this physically can be viewed as a sort of Ising type interaction. And what effectively this does is that it entangles your entire state. And if you're entangled in a particular way, which looks like a lattice, you get what is called the cluster state. And this cluster state is a sort of universal resource for measurement-based quantum computing, in the sense that by performing only measurements on the local qubits, you could get in principle, of course, and by performing these measurements in a specific order and applying specific directions, you can get in principle any unitary which you want. Just an example of the way the computation is carried out in this cluster state. So like I said, our results apply for the circuit model. So what I defined previously is not redundant. We will talk again about the circuit model and derive some stuff concerning this circuit model. But for the application, for like the demonstration of quantum speedup, we will actually use this formalism, and we will present a direct translation between the circuit model and this formalism. So one particular example here is that the case of two qubits which are entangled together by a controlled Z rotation. So this is initialized to the plus state, this is initialized to the plus state, and you perform a measurement at an XY angle of alpha. And so what we're interested in, if you remember, is sort of random distribution of the unitary group. But where does the random kick in actually? The random kicks in by the fact that we don't correct for our measurement results. So what we do, normally when you correct for your measurement result, you either get this unitary, which is Hadamard and control rotation, or Hadamard and Z and control rotation. But if you don't correct for your unitary, for your measurement, effectively what you would get is this random unitary, where this M is a binary string, 0 or 1. So this same idea applied to larger graphs gives you larger random unitaries, right? With lots of different M's. And the different set of these random unitaries for the different sets of M are effectively what are the T-design in the end. Because like I said, the T-design is a sampling over some random set. The random set is provided by these DCMs, only applied to larger systems. And the probability is just the probability of getting a measurement out of quantum mechanics. And this is the way that you generate okay, so now that we've defined sort of the main technical formalisms of quantum computing that we're going to work with, I will define a notion which is a notion of classical simulability. So what does it mean for something to be simulable classically? And this is interesting from the point of view of developing a quantum sampler, in the sense, which samples from something efficiently that the classical distribution cannot sample from. And this is sort of one of the applications of this design. So, notions of classical simulability. So, there are two notions. The first one is the classical simulability of the strong sense. So when you say classical simulability in the strong sense, you require that given your circuit, your circuit on n qubits, and given your output, that your classical algorithm should compute the outputs of this quantum circuit. It should approximate them within m digits of precision by using a polynomial in m and n algorithm. So n is the size of the system, and what you're doing is that you have a quantum circuit, you have outputs of it, and what you're requiring the algorithm to do is to approximate these outputs. And so if your quantum device is universal under post-selection, so this is also like some sort of technical requirement, then your problem is in Sharp. The problem of approximating your output probabilities is in Sharp. And this thing, this class, Sharp, is believed to be hard even for quantum computers to do, despite what the experts on the internet. And so yes, quantum computers have their limitations. They cannot solve sharply hard problems, and so we're forced somehow to abandon this notion of strong sense. We cannot ask this from the quantum computer. And so we go on to a different notion, which is classical simulability in the weak sense. So classical simulability in the weak sense is the following. Instead of asking your classical algorithm to approximate, you actually ask it to sample x with probability x. This can be efficiently done quantum. Indeed, these measurement-based protocols are some sort of sampling, right? Because when you finish, when your protocol is done here, effectively what you would get is you would get a random unitary which is sampled either from HZ alpha or HZ alpha. So it's a random sampling. So this can be done quantumly efficiently. But what we will prove is that whatever this, what can be done quantumly efficiently cannot be done classically efficiently unless some foundational conjectures in computer science are wrong. So here are the conjectures we have to assume in our sampling problem. So why do we need in the first place to assume complexity theoretic conjectures? Well, because at the complexity theoretical level, there are some still unanswered questions in computer science, such as whether or not the polynomial hierarchy collapses, or whether or not P is equal to NP. But these things are widely believed to not be true. So P is different than NP, and the polynomial hierarchy does not collapse. And according to these, we somehow base a lot of complexity theoretic assumptions on. So these are, even if these are conjectures, but these are in some sense strong conjectures. So in the sense that they're believed to be true, but no one knows how to prove them. So conjecture one is that the polynomial hierarchy does not collapse to the third level. This can be something as a sort of weaker version than P and NP. And the second one is that approximating, okay, so maybe I say this in a, so if you have a quantum device, and this quantum device is what you would call universal, then in worst case, so you are guaranteed to find a probability, an outcome, which is hard, whose output is sharp P hard to approximate. But it isn't clear if this worst case, which means that there exists, actually extends to an average case, which means that if I don't take all the probabilities, I just take a fraction of these probabilities, will I find one which is hard? And so this is sort of the second conjecture that we assume. We assume that the average case of the problem is as hard as the worst case, and the motivation we take for this are particular symmetries in our circuit, which are linked to, for example, the symmetry of approximating the Jones polynomial in average case, or the symmetry of the translation of invariant Ising model. And so how do our proofs work? So you start out by supposing that you have classical simulability in the weak sense. So you have this sub-universal quantum device, this big graph state, in which this bigger version of this, in which you're doing measurements and you're doing them randomly. And you assume that you have a classical algorithm which can sample from this efficiently. And then you use some technical stuff, and you use some anti-concentration, which is a requirement which is provable for two designs. And here is where the unitary T designs come in. So they come in this anti-concentration. That was sort of the motivation for using them, plus some other technical stuff. And you transform your sampling problem to saying that this is equivalent to demanding that there's an algorithm in the third level of the hierarchy which approximates over refraction. So you input your two conjectures, which is that the polynomial hierarchy does not collapse, and that the average case is as hard as the worst case and short P, and so you get a contradiction. Good. So now that the basic framework language is defined, we can start actually to talk about the results. So like I said, the random circuit, which is the model we are representing, is a model in which you're choosing randomly your rules, and you're also choosing randomly your unity. And this unity is chosen from a set which has stringent requirements, namely that every element must contain its inverse, and that the elements of the unity are algebraic. So this is in general, I mean, there's nothing wrong with assuming this, but in our particular scenario, we want to generate by measurements. You can't always demand that your sets behave this way. You can't always demand that the sets which are generated by your random measurements are symmetric and are algebraic. And so this is what we've managed to remove here. So we've managed to remove partially this requirement. So instead of requiring that every element has its inverse, we just require that your set that you're sampling from is composed of two parts. A part which contains the inverse and algebraic, which is made up of 4 elements for technical reasons. And another part which is not necessarily algebraic, which not necessarily contains it inverted, but is universal, which is sort of not a very hard requirement because almost every case is universal. And so what we show that choosing randomly from this set, which is composed in this way, which is called a partially universal set, gives you also an efficiency design. Meaning that the conditions here are not necessary. And so it's sort of manifested the following theory. So for a particular random constant surface construction on any qubit, with two qubits randomly chosen from any partially invertible set. So somehow here in this any, we extend the class of sets we can use. Gives an efficient T design in this following depth. So this is T, this is N, which is the number of things we have, and this is epsilon, which is the precision of the design. And see, everything is polynomial and logarithmic, which is good from computer science point of view. And also, we remove the choice of, so if you see here, these rows here are selected at random, the algorithm. So actually, we also remove this requirement, and we just require that. So let me just explain a bit how this works. So you start out with this sets of units which are sampled from this partially invertible universal set, and then you apply a fix to 1, 2, and to those 1, 2 over k times, where k is and you apply them simultaneously to 3 over k times. And then, as the second step, you apply the k times to 2e, and you apply the k times to 4i, and then you repeat this thing an L number of times, and you see each of these scales efficiently in NFT, so the total thing scales efficiently in NFT. And you get at the end that the total unitary that is implemented on your system is a unitary of an epsilon approximate T design. So yeah, what's its usefulness? So like I said, let's remove the rigid requirements, maybe your sets must contain inverted and algebraic, and it extends the examples of structure. It has a nice translation to our service construction, which I should do this in MPC stuff. I'm going to show later about this. And it extends the family of measurements architecture to show what we call quantum speedup, meaning that the particular feature we use here is the provable anti-concentration. So this is how this links to the sampling problem. T designs have anti-concentration, and we need anti-concentration in our partner tools. So, that's basically it. So here you have this constructor, and here you have its MBQC equivalent in terms of graphs. So here is your graph state, which we call KGB. And I will show you later what it is, and you're arranging this graph state in blocks. And so looking more closely at what a single KGB is, it's just a multi-qubit cluster state, like multi-qubit measurements, repeated k times. Each of these multi-qubit measurements is called GB. And this is, for example, an example of what a GB can be. So this is an angle pi by 6 in the xy plane. This is an angle 0 in the pi xy plane. And this is some sort of irrational angle in the xy plane. And this thing, what I can show is that the random set generated by this is a partially invertible universal set. This and other examples. So you can replace, for example, here the pi by 6 by pi by 4. And you can even not use the irrational angle at the cost of maybe having a bigger graph space instead of having this 5-qubit gadget, have this sort of 8-qubit gadget. So this is the way it translates into MBQC. And now we're going to see how this MBQC gadget can be used in the sampling problem which we propose. So like I said, we propose the sampling problem to test for quantum speedup. So to show that something can be done efficiently quantumly, which cannot be done efficiently classically. And we don't want all the capacities of the universal fault-tolerant quantum computer. That's a crucial point because we have one short algorithm, for example. No, like we want some sort of sub-universal device, which is exactly this graph state fixed measurement, which gives you quantum advantage or quantum speedup. Whether this advantage can be used, it's useful for algorithms, I don't believe it is, but at least it's a proof of principle. Right. Right, so if you remember this guy here, so this n-cubic thing, which is formed of 2 qubit graphs, and each graph has k copies of this thing. When you measure everything non-adaptively, so you don't correct, and you can measure everything simultaneously, and you measure the output, so at the end you get n output qubits, which you don't measure. You measure these again in the computational basis, and what you show is that the probability of getting a particular outcome, assuming conjectures 1 and 2, the polynomial hierarchy and the average case, cannot be sampled from by a polynomial time classical algorithm. So it's either that the classical algorithm takes exponential time, or that these assumptions are wrong. And either way, it's very so if it takes exponential time, then it's cool because you have demonstrated quantum. So this is the efficiently comparable quantum device, which does something a classical device can't do efficiently. And if it's wrong, then something is wrong with classical computer. So, yeah. Right, so we discussed a bit these partially invertible universal sets. But what about, instead of requiring, what about removing completely the requirement of inverses and algebraic? So, like I said, that partially invertible stuff, it removes it only partially, because it requires that part of the set fulfills inverse algebraic, the other part not necessarily. So what if we choose that the entire set is in general generic set, meaning that it's any arbitrary universal set that not necessarily inverses or not necessarily. So we have two results in that direction. One of them, and each of them are relevant for any QC. So this is formalism. So one of them is this theorem 3, which we showed. So we showed that if your angles here are chosen from what is called the best measure, which is a uniform measure over a real number line, over a fixed interval of the real number, then everything but a set of measure 0, which means that with very high so this translates directly to whatever angles you choose here, then with very high probability, you would get that the random ensemble here is universal for quantum computing, and it's universal on this symmetry group where gamma is a positive integer. So this sort of gives you universality. And the second thing is also a technical result. So it says that, okay, how can I explain this in a easy way? There is none. But anyway, what you can take out from this is that there's a surprising property which relates to a technical operator which is called the moment superoperator. And this surprising property is that its second largest eigenvalue is independent of t. And if this holds, if this numerical result is actually true, then we can use theorem 1, the techniques we developed in theorem 1 for the partially invertible case. And we can use theorem 3, which is this guy here, the generic reference one. And we can use this numerical result of and you can show that generic reference with very high probability of any angle you choose, any choose, on polynomial size plus states, efficiently invertible plus states, gives the efficient design and orthogonal sample class, which is just sort of from this. Okay, so I think that's all I have to say for the technical stuff. Both the main message to the transcript. So these are some ongoing projects which I'm working on. So this is randomized benchmarking in disordered Hamiltonians, which is joint work with Ellen Derbyshire, Elise, and Elham Kashifi. And there's another project which I'm working on with Eli, which he can tell you more about tomorrow. It's on contextuality and quantum advantage in magic states. I'm working currently, like we have some results in this direction, on the error correction and verification of the quality of the graph states we get here. So we can generate these graph states and we can do these measurements and we can show that you're doing something efficiently quantumly, which you can't do classically efficiently. But what if noise comes into the model? So what if you assume decoherence? Then what would happen is something funky. You would actually get back to classical simulability. And so we're sort of trying to stay within this framework of random measurements and at the same time getting fault like recovering classical hardness. Which is interesting. We have no idea in that direction. We also, so like I said, my overall aim is to relax completely this requirement and get some genetic checks with PB. So I've sort of done that analytically now, but the idea is that it's not genetic. So I have an example of a set which does not contain inverses and is not composed of algebraic entries and would still give you an efficient T design. But I'm not sure about how common this set appears within the unitary group. So I'm still focusing on that. As well as, so this could be a particularly interesting direction at what is called the Solovay-Kitaev theorem. So the Solovay-Kitaev theorem is the sort of backbone of quantum computing. It says that in principle, if you have a universal set which contains inverses, then you can efficiently do any quantum computation using elements from this set and their inverses. But no one seems to believe that the inverse requirement is true, but no one knows how to prove it. I think using these stuff and the techniques we developed, that we may have a sort of perspective on how to attack this open problem, as well as I should start writing my thesis. Right, advertisement time. So I want you to do quantum stuff. So whoever is interested in knowing more about this stuff, I basically live on the 5th floor, so you can just pass by wherever you want. We can discuss, and if you're interested in even doing some more of it, and that would be amazing, because I hear you guys are awesome students in the shop. So yeah, this is basically the team. So we're currently Netica, this is our group website. Thank you for your attention, and this is my funding society. I acknowledge funding from it. It's Lebanese grants. So thank you very much. That's all I have to say.
So if anybody has any questions, please, now is your chance. So please feel free, ask anything you want, anything at all, okay? If you don't ask a question, I'm not going to believe you understood the whole presentation.
I'm waiting for your questions.
So ask any question.
When you drop the inverse,
No, it just means I don't require invertibility. The matrices are still unitary. But so the particular structure, the way this local random circuit works, is that it assumes that your set which you're sampling randomly from has inverses inside it. So what I managed to do partially is to eliminate this inverse, so you don't need inverses. And no one actually believes that you need inverses. Sorry? What zeros? In my but what do you mean by zero? How? But the oh right. So what you're saying is that no. Every one of these, so we're still inside unitary quantum dynamics. So what you're saying is that you believe that I made these unitaries somehow non-invertible in the sense that the inverse does not exist. No, it does exist. The inverse always exists. It's just not in the set. So not in the set of allowed operations. So that's the thing. But it always exists, of course, because we're still in the unitary group. Yes? Sorry, can you?
What do you mean by universal system?
Very good question. What I mean by universal system is, in principle, a system which can perform any quantum computation. So basically, on the mathematical level, what this means is a set of finite unitaries such that taking products of these unitaries can get you to arbitrary precision within any other unitary which you want. So it's the ability to perform any type of unitary that you want. And since, like, closed system quantum mechanics is unitary, then that means that you're getting any quantum operation which you want. Yes? Yes?
Okay, you said something about distribution of pairs, T times, K times, and L times.
Okay, good. Yeah, yeah. So this guy. Yeah, so in theorem 1, what we show is that repeating, so okay, let's maybe go back to here. So this thing has a depth, right? The number of these layers, like this is layer 1, this is layer 2, for example, this is layer 3, etc. So the number of these layers is called the depth, like the number of unitaries you choose. And so what we say here is that the number of layers you need is something like n cubed times t squared plus log of 1 over epsilon. And so here, if you repeat this order n squared times t times, and you repeat this order n squared times t, and you repeat all of this n times t, you would get n cubed times t squared. So it's just getting the number of repetitions you need. I'm just explaining what you need to repeat, where you need to repeat it, and how many times you need to repeat it. So here I have to repeat 1 and 2 and 3 and 4 n squared t times, and then I have to repeat 2 and 3 and 4 and 5 n squared t times, and the whole thing I have to repeat it n times t times, which gives you n cubed t squared. If you're asking about, oh, sorry, yeah.
When you're talking about temperature, what do you mean by temperature?
Temperature?
K system, what's temperature?
I'm not here, so what, temperature?
Yes, thermalization.
Thermalization, okay, yeah. So it's a sort of, so I don't know if you're familiar with what is called canonical typicality. So this is a phenomenon by which if you look locally at your quantum state, then it would behave as if it's globally in a Gibbs state. And so what was shown in this direction is that if you're applying a Haar random unitary on this thing, then it would exhibit canonical typicality. But the idea is that this Haar random unitary, because the Haar measure is inefficient, probably needs exponential times, which means that thermodynamic equilibration requires exponential time. So for a system to reach thermodynamic equilibrium, it requires exponential time. But this is clearly not true, right? Because in real life, we see things which thermalize very quickly. And so one of the possible explanations is that this evolution is actually governed by the time, which remains the Haar measure. So that's sort of where because the design is efficient. So that's sort of where the design stuff comes. Yeah. So you're asking about temperature and yeah. So you can always consider this. So what I'm saying here is like independent of computation. This is like the result of physics. So what I'm saying is that I have a big closed system, because any system which is open, you just assume that as like a big system which is closed. So I'm just assuming that this bigger system which is closed is undergoing a unitary evolution which is given by a T-design, and then I look locally at these open systems and I see that they behave as if they're a Gibbs state. And so this is a sort of interpretation of equilibration, but this is not a quantum computing this is not useful for quantum computing. This is just an application to this formalism of T-designs. So where possibly T-design can come into this. Yes? No relation with Russian intelligence. I always wanted to say that. Okay, KGB. Yeah, here it is. Here it is. Yeah.
You said that the bits or the qubits that are repeating are the system key and I'm repeating it over and over again k times.
Yes.
But the example doesn't show that every one is different than the other.
Sorry. So here it's different than here.
It's different than the example.
The example is different than this.
Yes, the example
Yes.
It's not the same. So I didn't quite understand.
Okay. So just think of this as general measurements. Like just think of it not necessarily by biological features and by biology, whatever. But this is just a particular example of the way you can choose these such that you would get a partially invertible set. But yes, there exist other choices. But the reason I put these in blue means that those are like general things you can do, and particularly this is an example of one of the ways they can do it. But the crucial thing is that these things are fixed. So all of these measurements are fixed. So just the definition of fixed measurements, which is over a big graph state, and we're seeing the outcomes of this picture. So you know beforehand what you should measure. It's fixed. You're choosing to measure. You just measure everything non-adaptive. You measure simultaneously, and what you will get is a probability distribution which cannot be simulated scientifically.
So this fixed.
Yes.
Rather than one.
Yes. All right. Thank you.